So students, today we will start a new chapter, and that is Binomial Theorem. So what are binomials? It is a polynomial with two terms. I know to see this you have to tilt your head a little bit. So polynomial, it's a polynomial with two terms. For example, a plus b or x plus 2y, and so that is what basically it is on binomials, and we are going to study the whole chapter this time. Now to start with, I'm going to introduce to you a new triangle, and that is called it's called something. We'll come to know that. But for now, I want you to remember this. Go back to your previous classes and remember this. What is a plus b whole to the power 0? It is anything to the power 0 is 1. What about a plus b whole to the power 1? That is 1a plus 1b. What is a plus b whole to the power 2? That is 1a square plus 2ab plus 1b square. I know that you need not write the 1, but I am writing the 1 here because of some one reason which we'll come to know later. So what about a plus b whole to the power cube? It will be a cube plus 3a square b plus 3ab square plus b cube. Now for those who don't know what is a plus b whole cube, no need to worry at all. Just multiply these two things. You know what is a plus b whole square already, so multiply that with a plus b and you get this thing. Now what about a plus b whole to the power 4? You can find that by multiplying these two things, a plus b and a plus b whole cube, and you get a to the power 4 plus 4a cube b plus 6a square b square plus 4ab cube plus 1b to the power 4. What about a plus b whole to the power 5? That you can get by multiplying these two, or this and this, a plus b and a plus b whole to the power 4. You can multiply, so there are many ways of getting it. Now what is the answer for that? 1a to the power 5 plus 5a to the power 4b plus 10a cube b square plus 10a square b cube plus 5a b to the power 4 plus 1b to the power 5. Now if I am taking all the variables off and keeping only the coefficients, see what happens. 1 1 1 1 2 1 1 3 3 1 1 4 6 4 1 1 5 10 10 5 1. You see a triangle here, and this triangle is not a simple triangle. It has a lot of applications, and this triangle is called Pascal's triangle. So I'm drawing this is an expanded version of the triangle. So this triangle is not just made by binomial expansions. Just to make this triangle, you don't have to know binomial expansions. You don't have to do all a plus b whole cube square 5 and 6 and all. What you have to do is just addition. Let me show it to you. 1 plus 2 is 3. 6 plus 4 is the number below it, 10. 21 plus 35 is the number below it, 56. Do you see how this triangle is made? Imagine zeros wherever there is nothing, imagine zeros. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 0 is 1. So do you get it? This triangle, is just made by adding the numbers on top of it. And that numbers, coincide with what we get when we apply binomial expansions. When we expand binomials, and that is a wonder. And that's not just it, let us go to next wonder. Wonder number 2. So I'm writing few numbers of the Pascal's triangle, and I'm going to add the digits horizontally and see what I'm gonna get. 1 2 4 8 16 32. Do you find anything in these numbers? These numbers are actually the powers of 2. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. Do you see that? Now, that is not just it. So what do we see from here? We see that every row in the Pascal's triangle is a power of 2. So this is the 0th row, this is the first row, this is the second row, the third row, fourth row, fifth row. So the row counting starts from 0, by the way. 0th row, first row, second row, it goes like that. So 2 to the, so you take the number 2 and as the power you put the row number. So this is the 5th row, so I am putting 2 to the power 5. This is the 0th row, so I am putting 2 to the power 0. And you get the sum of all the digits in that number, in that row. Okay, now let me go to wonder number 3. I'm going to apply the same triangle. Now instead of adding them, I'm going to join them together horizontally. So what do I get? 1, 11, 121, 1331, 14641, 1510, 1051. Now, do you see anything in these numbers? These are the powers of 11. 11 to the power 0 is 1, 11 to the power 1 is 11, 11 square is 121, 11 cube is 1331, 11 to the power 4 is 14641. Oh wait, but here there is an issue. 11 to the power 5 is not 1510, 1051. So is it a problem with the Pascal's triangle, or is it are we looking at it in a wrong way? So let us see. You take an example, take this number for example, 1032. How do we really write that? How do we really read that number? What is the standard way of reading that number? 1032, right? Now, how do we get that 1032? By applying the places. Ones place, tens place, hundreds place, thousands place. 1 into 1000 plus 0 into 100 plus 3 into 30 plus 2 into 1. 10 to the power 0 is 1. So this is how we actually read the number. I mean read the standard. This is the standard way of reading the number. Now applying the same thing to this row, what do we get? 1 into 1's place, 5 into 10's place, 10 into 100's place, 10 into 1000's place, 5 into 10,000's place, 1 into 1 lakh place. Now you multiply this one, and add this. 1 into 10 to the power 5 plus 5 into 10 to the power 4 plus 10 into 10 cube plus 10 into 10 square plus 5 into 10 plus 1 into 1. You will get 161051, and that is 11 to the power 5. So what do you understand? So not only that, you take any number, the previous numbers, 11 to the all these numbers, these numbers also follow the same rule. Take 121 for example. This is 1's place, 10's place, 100's place. So 1 into 100 plus 2 into 10 plus 1 into 1. That is 121. So you get that this applies everywhere. So what do you see? What do you see? In every row of a Pascal's triangle, there is the powers of 11. When you write them together, or when you write it as a one, when you write all these digits as one number, you get powers of 11. So that is another wonder. Now that's not it. That's not just it. Wonder number 4. Take a coin. Okay, sorry, that is another one. I got confused. But anyways, before that, I'm going to shade all the even numbers. Okay, all the even numbers I'm going to shade. What happens? This happens, and I know that it doesn't look like much, but you see that there's a pattern, right? Now suppose I'm taking a bigger Pascal's triangle and do the same thing. It will look like this. What do you see here? Do you see a pattern? Do you see triangles in between? Here there's a triangle, here there's a triangle, here there's a triangle, here there's a triangle. Yes, you see that. And this type of triangles are called Sierpinski triangle. So let me show you what that type of triangles are. This is called Sierpinski triangle, and Sierpinski triangle is made by putting drawing triangles in top of another triangle. Okay, so you take this. So look at this. Wherever there is a top facing triangle, wherever there is a triangle looking up, I'm going to draw a triangle looking down. So it is, see, when I increase it, it will be like this. So here there are three top facing triangles, three upward looking triangles, and I'm going to draw three bottom facing. Wherever there is an upward facing triangle, I'm going to draw a bottom facing triangle. So it will be like this. Then if I go one more, wherever there is top facing, I'm going to draw bottom facing. So like this. Now here there are top facing triangles, here, small, small. I'm going to draw small bottom facing triangles inside that. Again, and again. Do you see? It can go on till infinity. If I can zoom this more and more, it can go till infinity. So this pattern is called Sierpinski triangles, and this is what we actually see in this. So when we do a Pascal's triangle, when we get a Pascal's triangle, when we just cover the event terms, we get such a pattern. So do you see how many things are there in this one triangle, which is just made up by adding numbers? That is what you should remember. This triangle is just made by adding numbers, and you see all these things, coming from that. Now, that is not just yet. Not just yet. Let us come back. Wonder number 5. Again, the Pascal's triangle. Take a coin. Now it's the time of a coin. So toss a coin. And what do you get? You get, of course, heads and tails. So this is a group. This is all the probabilities. I have just grouped them up. So if I toss only once, I get heads or tails. So the probability of getting a head is 1. Probability of getting a tail is 1. If I toss 2 times, I can get 2 heads. 1 head, 1 tail, 1 tail, 1 head, 2 tails. So the probability of getting 2 heads is only 1. The probability of getting 1 head, 1 tail is 2, because either I can get head or tails or head. Then the probability of getting both of them tail is only 1. And the same thing for 3 tosses and 4 tosses. 1 double 3, 1 1 4 6 4. And what do you see? These are the numbers in the Pascal's triangle. So look at this, 1 1 1 2 1 1 3 3 1 1 4 6 4 1. That is what you exactly see in the Pascal's triangle. So you see that it even covers the area of probability. So it covers Pascal's triangle covers the area of geometry. We just saw that Sierpinski triangle. It covers the area of algebra. We saw that in the binomial expansion. It covers the area of probability. We just saw it now. So it covers the area of patterns, sequences and series. Patterns, that chapter I have not yet studied. It is yet to come, but I'm just telling you. So it covers a lot of areas. Do you see that? Now, you would be thinking, sir, the first number is not there. Number 1 is not there. It starts from 1 1. No, 1 is also there. That is, toss is 0. That means if you don't toss at all, it won't change. There will be only one probability. What is there up looking at you, that will be the probability. So there is only one, and that is this one. Okay. Wonder number 6. Okay. My PPT tells to teach that only in the next class. So then we will meet in the next class. Bye bye.